In this lesson, we're going to talk about graphing rational functions. All right, let's start off with the definition of a rational expression. So a rational expression is the quotient of two polynomials with a non-zero denominator. Remember that we cannot divide by zero, so that's undefined in math. So a rational function is a function that is defined by a rational expression. So here we've set up a little function. We have f of x equals p of x over q of x, where again, q of x is not equal to 0. So p of x and q of x, those are polynomials, where again, q of x, this guy in the denominator, is not 0. So the domain of a rational function consists of all real numbers, except those for which the denominator equals 0. So let me give you one example here. This is f of x equals x minus 3 over 2x squared minus 13x plus 15. If I ask you for the domain for this guy, how would you get it? Well, again, it's all real numbers except those that make the denominator 0, because you can't divide by 0, that's undefined. So what you want to do is you want to take this right here, this denominator, which is 2x squared, and then minus 13x, and then plus 15, and you want to set it equal to 0, and you want to solve that equation. So the solutions that you get for this, again, make the denominator 0, so you have to exclude those values from the domain. And we can solve this with factoring. This is a pretty easy one overall. This is 2x squared, so I'm going to put a 2x here and an x here. Notice that this is a minus and this is a plus, so that means I want a minus here and a minus here. And then for this 15 right here, just think about the positive factors. You have 1 and 15 or 5 and 3. So 1 and 15 is not going to work. You're going to need to use 5 and 3. So what you want is a 5 here and a 3 here. And then when you check this, your outer, 2x times negative 5, that's negative 10x. And then your inner, negative 3 times x, that's negative 3x. When you add your outer and your inner, so negative 10x plus negative 3x, that's going to be negative 13x. Okay, so what we're going to do is use our zero product property. So 2x minus 3, this factor right here, we're going to set that equal to 0. Then or, we're going to take this factor, which is x minus 5, we're going to set that equal to 0. So we're going to add 3 to both sides of the equation, and this right here is going to cancel. We're going to get 2x is equal to 3, and then we're going to divide both sides of the equation by 2, and so let's cancel this with this, and we get x equals 3 halves. Over here, let's add 5 to both sides of the equation, so this cancels. We're going to get that x is equal to 5. So you get x equals 3 halves, or x equals 5. Let me actually write that like this. I'm just going to put x is equal to 3 halves. I'll just put a comma, and then you could say x could also be 5. So these two values right here would make the denominator of that rational function 0, so they have to be excluded from the domain. So when we come back up and write our domain here, we're just going to say it's the set of all x such that x is not equal to, you would have 3 halves, and then also 5. All right, let's take a look at graphing y equals 1 over x. So the most basic rational function with a variable in the denominator is this y equals 1 over x, or f of x equals 1 over x, if using function notation. This function is known as the reciprocal function, which we studied earlier in the course. We did a lesson on parent functions, and we also did quite a few lessons where we looked at graphing transformations. So we should know the graph of f of x equals 1 over x at this point. So the reciprocal function pairs every non-zero real number with its reciprocal. Since x is in the denominator, x can't be 0. All right, so what we're going to do now is just review the graph of f of x equals 1 over x. We're also going to talk about the features of f of x equals 1 over x. So we'll just kind of do those together. The idea here is that we've already seen this graph a lot. Again, when we're doing graphing transformations, we use this a lot as the parent function. And when you're in this section, the first problems that you get, you can graph them using graphing transformations. And if you know these 6 points that I'm going to go through here, it's very easy for you to complete those problems. So essentially, the first point I have here is negative 2 comma negative 0.5, or you could say negative 2 comma negative 1/2. Then you have negative 1 comma negative 1, and then negative 0.5 comma negative 2, or of course you could say negative 1/2 comma negative 2. And then up here you have 0.5 comma 2, or again you could say 1/2 comma 2. You have 1 comma 1, and then you have 2 comma 0.5, or again 2 comma 1/2. So this point, this point, this point, this point, this point, this point, that's really all you need, along with the fact that you have a vertical asymptote, which is x equals 0, and a horizontal asymptote, which is y equals 0. So if you know that, you can make this graph pretty easily. Then when you think about the features of your f of x equals 1 over x, again, just think about the graph that we just looked at. The domain is the set of all x such that x is not equal to 0. Again, what did we talk about earlier when we talked about the domain? Well, it's all real numbers except for those that make the denominator 0. How can I make the denominator 0 here? Well, I would just plug in a 0. So I would have to exclude 0 from the domain, but anything else is okay. Now, in terms of the range, that one's pretty easy to think about as well. Let's replace f of x with y, and then you could replace y with a 0, and you can think about why this is not possible. So this equation that I've just set up is going to be one that has no solution. When you think about this right here, this 1 over x, this is a fraction, and for a fraction to have a value of 0, the numerator needs to be 0, and the denominator needs to not be 0. Well, how can I get a numerator of 0 here when the numerator is 1? That's a constant, it's never going to change. So this right here, this 1 over x equals 0, that's impossible. There's no value for x such that 1 over x would be equal to 0. So this has no solution. So that means the range would be the set of all y such that y is not equal to 0. Okay, when we think about this part right here, so f of x equals 1 over x decreases on the intervals. Let me go back up. So just thinking about it, it's this piece right here. So this is where x is less than 0. So in interval notation, this piece right here, this is you're coming from negative infinity, going up to and excluding 0. And then also this piece right here. So this is anything greater than 0. We're also decreasing on that interval. So this would be anything larger than 0. Again, this is just going out to positive infinity. Then you have that the graph is discontinuous at x equals 0. Again, because we can't divide by 0, that's undefined. The line x equals 0 or the y-axis is a vertical asymptote. Then we have the line y equals 0 or the x-axis is a horizontal asymptote. And then the reciprocal function f of x equals 1 over x is an odd function. So again, we've talked about this a lot. The graph is symmetric with respect to the origin. Okay, so in this section, we're going to use something called arrow notation. If you take a Calculus 1 course, you're going to see this a lot. So this might be new for you, but it's really not that bad. It's just something you need to practice with. So first we have this f of x. This means approaches, or you could say goes to, when you see this arrow here. So this is negative infinity as x approaches 0. And then this right here, this little negative sign, that means from the left. So if you read this, it's y approaches negative infinity as x approaches 0 from the left. So that's what this is meaning right here. Then if you look at this one, you have f of x, or again y, approaches, this would be positive infinity as x approaches 0. This plus sign here, that means from the right. So this is from the right. So the reason we have to be specific there, if we come back up to the graph, and I'll also show you this with a table, think about this piece of the graph right here. So what we're saying is that y approaches negative infinity as x approaches 0, but we have to be very specific here. We can't just say approaches 0 here, because what if I'm approaching 0 on this side right here? Well, then the y values would approach positive infinity. So to be specific, we're going to include this notation here. We're going to put this little minus there up at the top. So that means from the left. So coming from the left, I'm talking about this guy right here. So coming this way from the left, as my x values get closer and closer to 0, my y values are, again, decreasing without bound. I'm approaching negative infinity. For this piece of the graph right here, as the x values get closer and closer to 0, well, now the y values are increasing without bound. So I'm approaching positive infinity. So again, I got to be specific. So for this one, we would say y approaches positive infinity as x approaches 0. Again, this is going to be from the right. So I want to make sure I put that plus sign right there to say from the right. So that's why we have this different notation here in case that's a little bit confusing. So another way to do this, and you'll see this in your textbook, is with using a table. So just another way to think about it. So you have f of x or y approaches negative infinity as x approaches 0 from the left. So using a table, you could just think about, well, here's 0 on the number line. If I'm to the left of 0, where the values are negative, again, I'm getting closer and closer to 0 coming from this side without touching it. So you have -1 here, but then you can get closer by saying -1/2, then you could do -0.1, then you could do -0.01, and so on and so forth. So what's happening is you're decreasing without bound, and your y values are approaching negative infinity as you get closer and closer to 0. You can get as close as you want, you just can never touch it. Then similarly, if we think about this one, so f of x or y approaches positive infinity as x approaches 0 from the right. So that's me coming over this way. Again, I have 1 here, but again, I can get closer by saying 1/2, then I could do 0.1, 0.01, so on and so forth. What's happening is as I get closer and closer to 0, the y values are now increasing without bound, so I'm approaching positive infinity. So putting these two things together, you could say in terms of absolute value. So remember absolute value, that takes something that's negative, it makes it positive. So the absolute value of f of x or the absolute value of y approaches positive infinity as x approaches 0. So this is either from the left or the right. And the reason we're able to say this is because of these absolute value bars here. So keep that in mind. So as x gets closer to 0, coming from either the left or the right, the y values in terms of absolute value, so that's the key here, get larger and larger. Since x can't actually be equal to 0, our graph will never intersect the vertical line x equals 0. As we have previously seen, this line is known as a vertical asymptote, so that's where that's coming from. All right, so for the next two, we have f of x or y approaches 0 as x approaches negative infinity. That's pretty straightforward. And then similarly, we have f of x or again y approaches 0 as x approaches positive infinity. Again, just coming back to the graph, you can think about it this way, or you can also use the table. I'll just do both with you. So think about this piece right here. What's happening to the y values or the function values as x increases without bounds? So in other words, what's happening as x goes to positive infinity? Well, the y values are getting closer and closer to 0. So we can say that y approaches 0 as x approaches positive infinity. Well, then if I look at this piece over here, where x is decreasing without bounds, so as x approaches negative infinity, you could say that y is also approaching 0. So we're going to say y approaches 0 as x approaches negative infinity. So again, you can also think about this with a table. You'll see this in your book. So you have f of x or y approaches 0 as x approaches negative infinity. So just thinking about that, x now we're thinking about as it decreases without bounds. So as we keep going this way on the number line, so you can see I have a little table here. So if you plug in something like negative 10 for x, 1 divided by negative 10 would be negative 0.1. And again, you can just make this more and more negative. So something like negative 100, you plug that in, 1 divided by negative 100, you get negative 0.01. And you're going to keep getting closer and closer to 0 without actually touching it as this guy gets to be a larger and larger negative number. Now, the other one, let me erase this, we have f of x or y approaches 0 as x approaches positive infinity. So this way is where we're going now. So as we increase without bounds, so we approach positive infinity. Again, it's a similar concept here. So 1 divided by 10, you get 0.1. Then 1 divided by 100, you get 0.01, and so on and so forth. You can just keep making this number bigger and bigger, and you're going to keep getting closer and closer to 0. So to summarize this, we can say f of x or y approaches 0 as, and again, this is why we can write this because of the absolute value bars, the absolute value of x goes to positive infinity, or you could say approaches positive infinity. So as x gets large in terms of absolute value, so as the absolute value of x goes to positive infinity, the y values get close to 0. So in other words, the graph will get closer and closer to the horizontal line, y equals 0, which is known as a horizontal asymptote. All right, let me give you a quick summary of the arrow notation, just in case it's not clear for you, because this is definitely going to come up in this section. And then again, if you get into calculus, you're going to see it a lot. So this right here means x goes to, or you could say approaches a from the left. When we say goes to or approaches, we're saying that it gets very, very close as you would like without actually getting there. In other words, we looked at x approaches 0 from the left. So coming from the left, we're approaching an x value of 0, but we're never going to actually get there. So that's what that means. Then this one is x approaches, or again, you could say goes to a, and this is from the right. So you would just change this like this, and you would say x approaches 0 from the right. Then the other two, we have x approaches or x goes to negative infinity. So we can say also that this is x decreases without bound. Then this one is x goes to or x approaches positive infinity. So in this case, you might hear x increases without bound. All right, so at the beginning of this section, you're going to be able to use graphing transformations to graph your problems. So this is going to be graphing transformations of y equals 1 over x. So you could say f of x equals 1 over x. So I have here a simple rational function of the form g of x equals ax plus b over cx plus d. So if you get something that looks like this, so something like g of x equals 2x plus 8 over x plus 2, you can use graphing transformations for this. Now, it might not be obvious how you're going to do that, but essentially, if you compare this to f of x equals 1 over x, before doing anything, you might be stuck. So what do I do? Essentially, you're just going to do long division, or in this case, you could do synthetic division to set the problem up. Let me put a little border here. You would say that this is 2x plus 8 divided by, remember, you want this in the form of x minus k. So we're going to go x minus a negative 2. Let me switch over the color here for that, so this is clear. And so essentially, you're going to set up your little synthetic division. So put your negative 2 out here, and then your 2 here and your 8 here. Drop down the 2. Negative 2 times 2 is negative 4. 8 plus negative 4 is positive 4. So this right here, again, it's 1 degree less. Well, we were working with a first degree, so 2 would just be the constant. And then this would be the remainder. So coming back up, let me get rid of this. And you can get rid of this for a moment. Let's just say this would be equal to, well, again, the quotient was 2. And then plus the remainder was 4. And you want to write that over your divisor here, or your denominator. So this would be x plus 2. Well, if I look at it like this, now that looks like something I can use graphing transformations for. If I put f of x equals 1 over x, and then g of x equals 4 over x plus 2, and then plus 2, what you'll notice is that you could write this as g of x is equal to 4 times f of, you would have x plus 2 there, and then plus 2. This 4 right here is giving me a vertical stretch by a factor of 4. This plus 2 on the inside, again, for horizontal transformations, you have to undo what's being done to x. So it's x plus 2. So to undo that, I need to subtract away 2. So this part right here means I need to shift left by 2 units, not right, left by 2 units, because you have to undo things on the inside. Then this plus 2 right here, that's going to mean me shifting up by 2 units. So if you have an x comma y on your original f of x equals 1 over x, when you go to g of x, it's going to be x minus 2, again, because we're going to shift left by 2 units, comma, 4y, again, you have a vertical stretch by a factor of 4, so you're multiplying y by 4, and then plus 2 because of the shift up by 2 units. So I'm just going to show you some points. These are, again, from earlier on, and you can go through and pause the video and just verify these, but essentially something like negative 4 comma negative 0.25, that's going to go to negative 6 comma 1. Negative 2 comma negative 0.5, that's going to go to negative 4 comma 0. Negative 1 comma negative 1, that's going to go to negative 3 comma negative 2. Then negative 0.5 comma negative 2, that's going to go to negative 2.5 comma negative 6. Then 0.5 comma 2, that's going to be negative 1.5 comma 10. 1 comma 1 is going to go to negative 1 comma 6. 2 comma 0.5 is going to go to 0 comma 4. And then 4 comma 0.25 is going to go to 2 comma 3. So looking at the graph, this is going to be for g of x equals 4 over x plus 2, and then plus 2. Again, just using graphing transformations to get these points. So you have negative 1.5 comma 10, negative 1 comma 6, 0 comma 4, 2 comma 3. So that's going to be for this branch right here. And then you have negative 6 comma 1, negative 4 comma 0, negative 3 comma negative 2, and then negative 2.5 comma negative 6. That's going to be for this branch right here. Now, in terms of the asymptotes, how do I know I have x equals negative 2 as the vertical asymptote, and then y equals 2 as the horizontal asymptote? Well, when you think about this, moving your vertical asymptote, that's going to deal with any horizontal shift that you have. In this case, the horizontal shift, again, because you have that plus 2 there, you need to undo that, so it's minus 2. You're going 2 units to the left. So normally, the vertical asymptote is x equals 0, or the y-axis. But again, because we shifted it 2 units to the left, now it's going to be x equals negative 2. Then in terms of the horizontal asymptote, again, normally that's the x-axis, or y equals 0. You're just going to look at your vertical shift, so that's plus 2. You're going up 2 units. So now that becomes y equals 2. So that's how you would get that. All right, now let's talk about another one that's common in this section. So graphing y equals 1 over x squared, or again, f of x equals 1 over x squared in transformations. So another very common rational function is y equals 1 over x squared, or again, f of x equals 1 over x squared if using function notation. So f of x equals 1 over x squared is even, meaning it has y-axis symmetry. So similar to the reciprocal function, the graph has a break. It is made up of 2 distinct branches. So coming down to the graph, again, this is one that we've seen before. So for f of x equals 1 over x squared, if you have an x value of either positive 2 or negative 2, you're going to get a y value of 1/4. Again, we know that squaring a number, if it's negative and you square it, you get a positive. If you square a positive, you keep a positive. So 1 over negative 2 squared, that's 1/4. Then 1 over 2 squared, that's also 1/4. So you get this point right here, which is negative 2 comma 0.25, and this point right here, which is 2 comma 0.25. Then similarly, if you have positive or negative 1 for the x value, you're going to get positive 1 for the y value. So negative 1 comma 1 and 1 comma 1. If you have positive or negative 1/2 for the x value, you're going to get 4 for the y value. So you have negative 0.5 comma 4 and then 0.5 comma 4. Then again, at an x value of 0, you're going to have undefined, because if you had 1 over 0 squared, that's 1 over 0, that's undefined. So you'd still have a vertical asymptote at x equals 0, and you'd also have a horizontal asymptote at y equals 0. All right, let's talk about the features of y equals 1 over x squared. So first and foremost, we have our domain, where we say the set of all x such that x is not equal to 0. Again, because we have this x squared in the denominator. When we look at the range, we would say the set of all y such that y is greater than 0. So again, y can't be 0. So if you look at y equals 1 over x, or you look at y equals 1 over x squared, in each case, y can't be 0. Now, in this case on the left, the first parent function that we looked at, your y values could be negative. And that's because you can plug in something negative for x there. And so let's say you had negative 1. 1 over negative 1 would be negative 1. So a point on this graph would be negative 1 comma negative 1. But for this guy right here, because of the squaring, you're not going to be able to get a negative for your y values. In other words, if I plugged in a negative 1 for x, Well, negative 1 squared is 1. 1 over 1 is 1. So now you get negative 1 comma 1. So that's the difference between the two. Now again, we just go back to the fact that it can't be 0 either, because if you plugged in a 0 right there for y, this equation has no solution. In order for 1 over x squared to be equal to 0, the numerator would have to be equal to 0 and the denominator would have to be non-zero. Well, in this case, the numerator is always going to be 1, so this equation has no solution. So the range here is going to be the set of all y such that y is greater than 0. When we look at this f of x, or again you could say y is equal to 1 over x squared, it increases on the interval, so here it's going to be anything less than 0. Again, coming back, so that's this piece of the graph right here. So when we're less than 0 in terms of the x values, we're increasing as we go from left to right. This guy right here, you're going to be decreasing, so this is anything greater than 0 in terms of the x values, so you're decreasing for that branch right there. So I have that f of x equals 1 over x squared, decreases on the interval, so this is anything greater than 0. The graph is discontinuous at x equals 0, and then the line x equals 0, or the y-axis, is a vertical asymptote. Now this one, the line y equals 0, or the x-axis, is a horizontal asymptote. Again, just coming back up here, think about what's happening to the y values as the x values approach either positive infinity or negative infinity. Well, what's happening is your y values are getting closer and closer to 0. Just think about this as y equals, again, 1 over x squared. Think about some really large number that you plug in there. So let's just say you take 10 or something like that. So 1 over 10 squared is 100, so that's 1 over 100, and that's going to be 0.01. Well, if I keep increasing the value for x, again, as I approach positive infinity, what's going to happen is your y value is going to get closer and closer to 0. It's never actually going to get there, but it's going to get closer and closer. So that's going to give me this horizontal asymptote, which is y equals 0, or again, this is going to be the x-axis. So the vertical asymptote of x equals 0 and the horizontal asymptote of y equals 0, that's exactly the same as when we looked at y equals 1 over x. Then lastly, we have f of x equals 1 over x squared as an even function. So again, we already know that the graph is symmetric with respect to the y-axis. All right, so like I said before, at the beginning of this section on graphing rational functions, you're going to get easier problems where you could sketch the graph using graphing transformations. So if we have something like g of x is equal to 2 over the quantity 1/2 x minus 1 squared, and then minus 1, you can graph that based on this f of x equals 1 over x squared. So as I talked about in the lesson on graphing transformations, if your coefficient of x is not 1, you can go ahead and factor that out. You don't have to, but if you do it, it's going to make it a lot easier. So I'm going to write this as g of x is equal to 2 over. So now we have the brackets here, again, for us to factor out the 1/2. So you pull that out, you have 1/2 times the quantity x minus 2, and then this whole thing is squared, and then you have this minus 1. So what I would do is write this in terms of f of x. So we would have g of x here is equal to, well, you have this 2, that's going to multiply your function here, so f of, again, think about what's being plugged in for x. You have this guy right here that's being squared. Well, what's being squared here? Well, it's going to be this right here. So this right here will get plugged in right there. So you're just going to copy that. So this is going to be 1/2 times the quantity x minus 2. Close all that down. And then you just have this minus 1 on the outside. So when you write it like this, it makes it easy to think about all the graphing transformations we're going to apply. Remember, you have to be very specific about the order. Vertical transformations and horizontal transformations do not impact each other, so those could be done in any order. But when you're talking about vertical transformations, they have to follow the order of operations. So in this case, you're going to multiply by 2 first, and then subtract away 1 second. When you talk about the horizontal transformations, those have to go in the reverse of the order of operations because you're undoing things. When you undo stuff, you go in the reverse order. So here you're going to end up multiplying by 2 first to undo this, and then adding 2 second to undo this. Like I talked about in the lesson on graphing transformations, when it's in factored form, you could just work left to right. That's why I spend the time to factor. So you could do this first, and then this one would be second, this would be third, and then this would be fourth. So the first thing we have is this multiplication by 2. Again, if it's a vertical transformation, it's very straightforward. So this gives me a vertical stretch by a factor of 2. Then when we come on the inside, again, for horizontal transformations, we're undoing things. So how do I undo multiplication by 1/2? I need to multiply by 2. So that gives me a horizontal stretch by a factor of 2. Then coming on the inside here, I have x minus 2. So to undo subtraction of 2, I want to add 2, so that's going to shift me to the right by 2 units. Then coming to the outside here, again, this is going to be straightforward because it's a vertical transformation. We have this minus 1 here. That's just going to shift me down by 1 unit. So if you have an x comma y on your graph, f of x equals 1 over x squared, when you get to your g of x, this is going to be 2x plus 2. Again, that's coming from this horizontal stretch by a factor of 2 done first, and then plus 2, that's coming from shifting right by 2 units. So 2x plus 2, and then comma, you have 2y minus 1. That's coming from the vertical stretch by a factor of 2. Again, that's done first, and then shifting down by 1 unit, that's done second. All right, so again, you can pause the video and do these on your own. I've pre-written this to make it a little bit faster. You have this -2, 0.25, which is going to go to -2, -0.5. You have -1, 1, which is going to go to 0, 1. You have -0.5, 4, which is going to go to 1, 7. You have 2, 0.25, which is going to go to 6, -0.5. 1, 1, which is going to go to 4, 1, and then 0.5, 4, which is going to go to 3, 7. All right, so looking at the graph, this is going to be for, again, g of x is equal to 2 over the quantity 1/2 x minus 1 squared. And then we have this -1 here. You see the points that I just talked about. So for this piece of the graph right here, you have -2, -0.5, you have 0, 1, and 1, 7. For this piece right here, you have 3, 7, you have 4, 1, and 6, -0.5. Now, you can get more points if you need them, but I think that's enough to get a good sketch going. You need to know this vertical asymptote is x equals 2, and this horizontal asymptote is y equals -1. Again, how do we figure that out? Well, essentially, you're just looking at your shifts. For the vertical asymptote, again, it's normally x equals 0 or the y-axis. What was the horizontal shift? Remember, we shifted right by 2 units, and we're going to see the vertical shift is down by 1 unit. So coming back, because we had a horizontal shift to the right by 2 units, instead of this being x equals 0, now it's going to be x equals 2 for the vertical asymptote. Instead of it being y equals 0, or the x-axis for the horizontal asymptote, the shift was 1 unit down, so now we get y equals -1. So if you have your vertical asymptote and your horizontal asymptote, you're good to go. When you sketch this graph, it's going to approach but not touch the vertical asymptote. So that's this right here and this right here. And then this is drawn to where it approaches but does not touch your horizontal asymptote there and there. And I know when you look at these graphs drawn by a computer, or even when you hand draw them, it's going to look like it's touching, but again, it's getting very close but not touching. That's why we have our asymptote there drawn as a dashed line, so you know that. All right, as we continue to work through this section, we're going to see harder examples that we can't graph using graphing transformations. So for those type of problems, you need a general procedure that you can use for graphing a rational function. So in order to work our way up to that procedure, we need to understand asymptotes and how to find asymptotes. And I'm just going to start with vertical asymptotes. So the line x equals a is a vertical asymptote of the function y equals f of x if y approaches positive or negative infinity as x approaches a. This is from the right or left. In other words, what we're saying is that if the absolute value of f of x, or you could say the absolute value of y, approaches positive infinity as x approaches a, again, this would be from the right or the left, then the line x equals a is a vertical asymptote. Now, again, when you read definitions like this, a lot of times it's not crystal clear until you start seeing examples. You can just relate this back to what we saw earlier. We had f of x is equal to 1 over x, and just think about it this way. So we already know that there's a vertical asymptote that is going to be x is equal to 0, and that's created because you cannot plug in a 0 for x. Division by 0 is undefined. But again, just using this approach here, we can say that the line x equals 0 is a vertical asymptote because y approaches negative infinity as x approaches 0 from the left. And then y approaches positive infinity as x approaches 0 from the right. So you can write it like this. You can also use this right here, which we saw earlier, if you want to combine things. So the absolute value of y is going to approach positive infinity as x approaches 0. Again, when you use this without the plus or minus up here, this means, again, like we said earlier, from the right or left. So just matching things up, this tells us that we would have a vertical asymptote at x equals 0. So we're just using that definition here. So a rational function can have 0, 1, or more than 1 vertical asymptotes. Then the graph of a rational function can never intersect a vertical asymptote. That's because the vertical asymptotes are being created because of division by 0. So at those x values, the function will be undefined, so you're never going to be able to intersect where you have a vertical asymptote. All right, so we're going to look at some summary images real quick. So this is for y approaches positive infinity as x approaches a from the right. So this right here is an x value of a, and you can see that as the x values get closer and closer to a, again coming from the right, the y values are increasing without bound or approaching positive infinity. Then over here, y approaches positive infinity as x approaches a from the left. So this right here, again, we're approaching an x value of a from the left. The y values are again increasing without bound or approaching positive infinity. Then similarly, we have y approaches negative infinity as x approaches a from the right. Again, this is an x value of a. As the x values get closer and closer to a coming from the right, the y values decrease without bound or approach negative infinity. Then on this one, we have y approaches negative infinity as x approaches a from the left. So as the x values are getting closer and closer to a, again, coming from the left, now the y values are decreasing without bound or approaching negative infinity. All right, let's talk about a horizontal asymptote now. So something like the line y equals b is a horizontal asymptote of the function y equals f of x if y approaches b as x approaches positive or negative infinity. So in other words, if f of x, or again you could say y, approaches b as the absolute value of x approaches positive infinity, then the line y equals b is a horizontal asymptote. So again, just like we did before, we can go back to the f of x is equal to 1 over x that we already know. This one has a horizontal asymptote, which is y equals 0. So again, using this definition and matching things up, your b value here is going to be 0 because we're saying that y approaches 0 as x approaches positive infinity. And then also y approaches 0 as x approaches negative infinity. Again, just matching it up with this definition. You can even use this one, which is a little bit easier to write. So you can put that y approaches 0 as, and you could just use absolute value here to make it into one statement. So the absolute value of x approaches positive infinity. Let me fix that symbol there. So matching things up, we can say our y equals 0 is a horizontal asymptote for our f of x equals 1 over x. Now, when we talk about a rational function, it can have at most one horizontal asymptote. When we talk about vertical asymptotes, you can have as many of those as you like. There's no limit. But with non-vertical asymptotes, so I'm talking about a horizontal asymptote, or what we're going to talk about later on, which is a slant asymptote, you can have at most one of those. You might have 0, but if you have one, it's only going to be 1. Then this one, the graph of a rational function can intersect a horizontal asymptote. So with a vertical asymptote, the graph can never intersect that. Your graph can't have a point there because that x value makes the function undefined. But with a horizontal asymptote, we're not going to see that because what we're thinking about is what happens to the y values as x gets really, really large, approaches positive infinity, or as x approaches negative infinity. So it's okay if it intersects the horizontal asymptote, as we'll see with some examples coming up. All right, so just to get a little visualization of what this could look like. So this is y approaches b as x approaches positive infinity. So again, as the x values increase without bound, so as we approach positive infinity, the y values are approaching a value of b. Then over here, y approaches b as x approaches negative infinity. So here we're talking about as x decreases without bound. So as we approach negative infinity, again, the y values are approaching b. All right, in terms of finding asymptotes, it's actually pretty simple overall. So for vertical asymptotes, I have here, we can find the vertical asymptotes by finding the values for x that make the denominator 0. So it's the same process as you would use for finding the domain. Take your denominator, set it equal to 0, and solve. The solutions to that equation, you're going to have x equals whatever the solution is or the solutions. Those are going to be your vertical asymptotes. For horizontal asymptotes, we need to think about what happens to our y values as x approaches positive or negative infinity. So this is a model you would see in your textbook. Essentially, the only thing you really need to pay attention to is the leading term here and the leading term here. You can forget about the rest of the stuff. It's not going to come up. Essentially, you have a sub n, x to the power of n. That's the leading term in the numerator. And then b sub m, x to the power of m. That's the leading term in the denominator. So that's what you want to make sure you understand. So n is the degree of the numerator and m is the degree of the denominator. So for the vertical asymptotes, again, if a is a 0 of the denominator, then the line x equals a is a vertical asymptote. So that's very straightforward. Take your denominator, set it equal to 0, and solve. That's how you're going to find your vertical asymptotes. Then for horizontal asymptotes, you have these 3 different situations. So first, if n is less than m, then there is a horizontal asymptote y equals 0 or the x-axis. So it's just that simple. In other words, what we're saying is that if the numerator has a lower degree than the denominator. So again, when we say n is less than m, n is the degree of the numerator, m is the degree of the denominator. Then this scenario here is if n is equal to m. So in that case, then there's going to be a horizontal asymptote, which is y equals a sub n over b sub m. Okay, so it's the ratio of the leading coefficients. So this guy over this guy. And you'll see an example of that and where that's coming from. So in other words, I have here, if the numerator and denominator have the same degree, y equals the ratio of the leading coefficients is the horizontal asymptote. Then lastly, if n is greater than m, then there won't be a horizontal asymptote. So in other words, if the numerator has a greater degree than the denominator, you just won't have a horizontal asymptote. You could have something called a slant asymptote or an oblique asymptote, and that's when the degree in the numerator is exactly one more than the degree in the denominator. And I'll give you an example of that here momentarily. All right, let's look at some examples. So we're just going to find the asymptotes. So f of x equals x minus 3 over x squared plus x minus 2. So if I want to find the vertical asymptotes, what would I do? I would take this denominator here, I would set it equal to 0, and I would solve. So coming down here, you have x squared plus x minus 2 equals 0. We can factor this as the quantity x minus 1 times the quantity x plus 2. So again, set that equal to 0. And then using the zero product property, you get this factor x minus 1, set that equal to 0, or this factor x plus 2, set that equal to 0. So the solutions would be x equals 1 or negative 2. So coming back up, you would have a vertical asymptote, which is x equals 1. And then you would also have one, I'll just put a comma, you'd also have one at x equals negative 2. Then thinking about the horizontal asymptote, would we have one? Well, the degree of the numerator is going to be 1. The degree of the denominator is going to be 2. Let me just circle this and circle this. So the degree of the numerator is less than the degree of the denominator. That tells us that the horizontal asymptote is going to be y is equal to 0. So that's pretty simple overall. Now let me show you a way that you can think about this. So this is something you would see in a pre-calculus textbook when they're explaining the concept. So what you're going to do is you're going to take the highest power, which in this case is x squared, and so you're going to divide everything by that highest power. So the way you can do that is you can multiply by 1 over x squared over 1 over x squared. Remember that this guy is equal to 1 as long as x is not 0. One thing about doing this technique, if you look at this guy right here, the original guy, it is defined where x is 0, but this guy right here that we're going to change this into is not defined where x is 0. That actually doesn't matter for our purposes here because we're only going to think about what happens to x as it goes to positive infinity or negative infinity. We're not really concerned with what happens when it's 0, so this is okay. So we're going to multiply this by, again, 1 over x squared over 1 over x squared. We go through the simplification and we get this. So if I think about what happens to this guy right here as x approaches, let's just do positive infinity, or you could do negative infinity, doesn't matter. It's going to be the same thing. Well, this guy right here is going to go to 0. This is going to go to 0. This is going to go to 0. And this is going to go to 0. So what would I have left in that case? If this is 0 minus 0, you would have 0. And then if this is 0 and this is 0, you have 1 plus 0 minus 0. Well, that's 1. 0 over 1 is equal to 0. 0 divided by any non-zero number is equal to 0. So that means that as x approaches positive infinity or negative infinity, this guy is going to approach 0 over 1, which is 0. That means that the line y equals 0 is your horizontal asymptote. Again, that's the long way to do it. You don't need to do it that way. Just remember the rule that if the numerator has a lower degree than the denominator, you automatically have a horizontal asymptote, which is y equals 0 or the x-axis. All right, let's just verify what we found using a graph. Again, I left you a link for this on Desmos. So this is going to be for f of x equals x minus 3 over x squared plus x minus 2. So first we have this vertical asymptote of x equals negative 2. And we can just use this as an example to think about our definition of a vertical asymptote. First off, we know that this is created because if you plugged in a negative 2 for x in this function, you would get division by 0, which is undefined. So that's why you get this guy right here. Additionally, if we think about what's happening to the y values as x approaches negative 2 from the left, well, this guy is approaching negative infinity. So y approaches negative infinity as x approaches, this would be an x value of negative 2 from the left. So again, as we get closer and closer to an x value of negative 2 coming from the left, the y values are approaching negative infinity, or you could say we're decreasing without bound. Then additionally, y approaches positive infinity as x approaches negative 2 from the right. So as I'm approaching an x value of negative 2, again, coming from the right, I am increasing without bound, or the y values are approaching positive infinity. So following the definition of a vertical asymptote, that tells me that I have a vertical asymptote at x equals negative 2. Now you could use a similar thought process for this guy right here, which is the other one we found, which was x equals positive 1. So that's also a vertical asymptote for us. Now additionally, we're going to have a horizontal asymptote, which in this case is going to be the x-axis or the line y equals 0. So for this part of the graph right here, you can see that as the x values decrease without bound, so as they approach negative infinity, the y values get closer and closer to 0, but they don't get there. Then for this piece right here, you're going to notice that we actually cross over the x-axis. you have an x-intercept here, which is 3, 0. That's okay with a horizontal asymptote. Again, we're only thinking about what happens as x gets really, really large, so approaches positive infinity, or what happens as x approaches negative infinity. So even though this crosses over here, as you get really, really large in terms of the x values, the y values are getting really, really close to 0. So that's why y equals 0 is a horizontal asymptote. All right, let's look at another example. So here we have f of x equals 4x squared minus x minus 4. This is over 2x squared plus x plus 1. So let's start with the vertical asymptotes. So take the 2x squared plus x plus 1, set it equal to 0, and solve. And what you're going to find, again, you can use the quadratic formula for this, you get two non-real complex solutions. So you get x equals -1 plus or minus I times square root of 7 over 4. So if this happens, really when you think about the domain, it's all real numbers. There's no real number that I can plug in for x such that the denominator would be 0. And when we think about the domain, it's all real numbers except those that make the denominator 0. Well, there are no real numbers that make the denominator 0, so it's all real numbers. So when something like this happens, you would say that there's none. You don't have a vertical asymptote because you can plug in any real number that you want. You're not going to get division by 0. If you want to guard against this and you want to go more quickly, you don't have to actually go through and get the zeros in this case. Again, if you notice that the discriminant, which is b squared minus 4ac, is negative, you know you have two non-real complex solutions, and you could just stop and say, I'm not going to have any vertical asymptotes. So if you plug in, again, a is 2, b is 1, c is 1, to this part right here, you would get x equals -1 plus or minus the square root of 1 squared minus 4 times 2 times 1 over 2 times 2. Well, if you go through and simplify, now you have x equals -1 plus or minus the square root of 1 minus 8 over 4. Well, this right here is going to turn into -7 right there, and you could just stop. You know that you're going to end up with two non-real complex solutions. Again, as we talked about earlier, it's x equals -1 plus or minus I times square root of 7 over 4. Now let's talk about the horizontal asymptote. And in this case, the degree of the numerator, which is 2, is exactly the same as the degree of the denominator, which is also 2. So in this particular situation, you want to take the ratio of the leading coefficients. So in other words, 4 over 2. So y equals 4 over 2, which is equal to 2. So y equals 2 is the horizontal asymptote. Again, that's the quick way to do it. If you want the long way, again, we're going to use our trick where we're going to take the highest power of x, which is x squared. And so we're going to multiply this by 1 over x squared over 1 over x squared. And that's just going to be used, again, so we can think about things. Well, what happens as x approaches positive infinity, so it gets really, really big, or negative infinity? So you can think about, well, this guy right here, this 1 over x is going to go to 0, 4 over x squared is going to go to 0, 1 over x is going to go to 0, and 1 over x squared is going to go to 0. So what are you going to be left with? You're going to be left with 4 over 2, right, which is the ratio of the leading coefficients. So as x approaches positive infinity or x approaches negative infinity, your y values are getting closer and closer to 2. So just coming down to the graph to verify this, again, this is the f of x equals 4x squared minus x minus 4 over 2x squared plus x plus 1. You'll notice that you don't have any vertical asymptotes, again, because this guy right here, if you set it equal to 0 and solve, you get two non-real complex solutions. So there's no real number I can plug in for x such that the denominator would be 0. And so again, you're not getting a vertical asymptote in that situation. In terms of the horizontal asymptote, again, it's y equals 2. So it's this line right here. So you'll see that as x increases without bound, as it approaches positive infinity, we're getting closer and closer to a y value of 2. And then over here, we actually cross through this line y equals 2, and that's okay. You can do that with a horizontal asymptote. You have this point -2, 2 where that happens. And again, as you think about the x values approaching negative infinity, well, the y values now are approaching 2. So that's why we get our horizontal asymptote, which is y equals 2. All right, let's take a look at another problem. So here we have f of x equals 2x squared minus 5x plus 4 over x minus 1. So in this case, for the vertical asymptote, it's going to be real simple. You're just going to take x minus 1, set that equal to 0 and solve. And of course, you just add 1 to both sides. You get x equals 1. So let's put x is equal to 1. For the horizontal asymptote, this degree right here in the numerator, that's going to be a 2, is greater than the degree in the denominator, which is going to be a 1. When that happens, you will not have a horizontal asymptote. You can just say that there's none. When it's exactly one more, you're going to have a slant asymptote. So I'm going to show you that in a moment. For right now, let me just show you why we can say there's no horizontal asymptote. Again, just using the same thought process. So we start with this guy right here. And again, the highest power of x is x squared. So we use our trick. We're going to multiply by 1 over x squared over 1 over x squared. Again, we're just using this to think about what happens as x approaches positive infinity or negative infinity. Well, we can see that this guy right here is going to go to 0. This one would, and this one would. Okay, well, that's a problem for us because as x approaches positive infinity or negative infinity, what we're getting is 2 over 0, which is undefined. So what you can say is that y does not approach any real number as the absolute value of x goes to infinity. We will not have a horizontal asymptote in this situation. So this is going to occur when the degree of the numerator is greater than the degree of the denominator. If you look at the graph, you can verify this. This is f of x equals 2x squared minus 5x plus 4 over x minus 1. So you do have this vertical asymptote, which is x equals 1. So we have that guy right there. But you see that you don't have a horizontal asymptote. Now, you'll notice that I have another asymptote here, which is the line y equals 2x minus 3. I'm going to talk about where this is coming from in a moment. This is called a slant asymptote. Some people also refer to this as an oblique asymptote, but I'm just going to call it a slant asymptote. So for a slant asymptote, we previously stated that when the degree of the numerator is greater than the degree of the denominator, we will not have a horizontal asymptote. If, however, the degree of the numerator is exactly one more, and that's the case we have here, in our example, the degree of the numerator is 2, the degree of the denominator is 1, so then the degree of the denominator, then there will be a slant or oblique asymptote. Now, the way you get this in this situation is with some long division. In this particular case, we can use synthetic division because the denominator or the divisor here is of the form x minus k. So we can just take this 1 as the k value. Again, so you write that right here, and then you take 2, negative 5, and 4, and you can set up your synthetic division. So you drop this down. So 1 times 2 is 2, negative 5 plus 2 is negative 3, 1 times negative 3 is negative 3, 4 plus negative 3 is 1. So this right here is going to be the coefficient, again, dropping this by 1 degree. If this is squared, then this becomes to the first power. So you get 2x minus 3, and then plus this 1 right here is the remainder, and you put that over your divisor. So 2x minus 3, and then plus 1 over x minus 1. So looking at this, you can think about, well, what happens, just think about it in this form right here, what happens as x goes to positive infinity or negative infinity? Well, this piece right here is going to go to 0 because 1 over x minus 1, if x gets really, really large, you have 1 over some really, really big number, and that's going to go to 0. And the same thing would be true if x approached negative infinity. So this is going to approach 0. So what you're left with when that happens is just the 2x minus 3 part. And that's why when you come back to the graph, you see you have this slant asymptote, which is y equals 2x minus 3. All right, let's talk about holes in your graph. Some people call these removable discontinuities. So up to this point, we've only seen rational functions that were reduced to lowest terms, or you could say simplified. If we have a factor that can be canceled between the numerator and the denominator, we can do so, but only for values of x for which that common factor is not 0. Let me give you an example of this. So we have f of x equals 2x cubed minus 4x squared minus x plus 2 over x minus 2. So let me just factor the numerator. I'm going to put a little border here. We'll come back up in a moment. So if you have 2x cubed minus 4x squared minus x plus 2, well, from the first 2 right here, you could pull out a 2x squared. Inside, you're going to have x minus 2. From the second 2, you could pull out, let's just do negative 1. So inside, you would have x minus 2. So you'll notice that you have a common binomial factor of x minus 2. And so let's go ahead and pull that out. So that's going to come out here. So you're going to have this x minus 2 like that. Let me move this down a little bit. And then what's going to be left? You're going to have this 2x squared right there, and you're going to have this negative 1 right there. So we're going to have 2x squared and then minus 1 like that. Okay, let me get rid of all this. We're going to use this to rewrite things. So I'm going to say this is equal to, so I have the quantity x minus 2 times the quantity 2x squared minus 1. Okay, let me get rid of this. And actually, let me move this down. So this is over your x minus 2. So it's obvious at this point that you can cancel this with this. But there's an issue with this, and again, we talked about this earlier on in the course. When you think about what's going to be produced here, you're going to get 2x squared minus 1. So this function and this function are the same, except for where x is 2. Because if you look at this original rational function here, x can't be 2. If you plug in a 2 here, 2 minus 2 is 0. Division by 0 is undefined. If you plug in a 2 here, it's actually okay. 2 squared is 4. 4 times 2 is 8. 8 minus 1 is 7. There's no issue. So what you have to make sure you do is carry over any restrictions from the original rational function that are not in the new one that you create from simplifying. So the way you do that is you're going to put a little comma and you're going to say for x is not equal to positive 2. So you're carrying that over. So when you sketch the graph of this guy, you're going to graph f of x equals 2x squared minus 1, but where x would be equal to 2, you're going to put a hole. So that's going to look like this. This is f of x equals 2x squared minus 1, where x is not equal to 2. So this guy, if you look at where x is 2, you see that we put a little hole in the graph. So that would be 2 comma 7 on the normal graph for just f of x equals 2x squared minus 1. But on this graph, again, because of where it came from and because of the fact that we have to carry that restriction over, you're going to put a hole in the graph to say, hey, it's not going to be defined here. I gave you a link for this on Desmos. If you click on that link, you're going to need to take your mouse and actually put it directly over where the x value is 2, and then it's going to show you that 2 comma undefined there. If you don't mouse over it, you won't see it. So it's not obvious unless you take that step. All right, before we get to the procedure on graphing a rational function, we need 2 additional pieces of information. So the first thing is going to be the behavior of graphs of rational functions near vertical asymptotes. So we're going to let f of x be a rational function that is defined by a rational expression in lowest terms. That's actually important here. That means that this guy is simplified. So in other words, we cannot cancel a common factor between the numerator and the denominator. So we're not going to have a hole in this situation. So if n, which will be our exponent, is the largest positive integer such that, again, you have this x minus a, this is a quantity raised to the nth power. Again, this is going to be a factor of the denominator of your f of x. So the graph of our rational function will look different based on whether the n value is even or odd. And we've actually seen this already, because if you think about something like f of x equals 1 over x squared, it looks like this guy on the left. And if you went to Desmos and you typed in f of x equals negative 1 over x squared, you're going to get what looks like this guy on the right. So what we're saying is that basically, if you have a vertical asymptote, let's just say it's x equals a in this particular case. Well, if what led to that was a factor, so in the denominator, x minus a, let's just say it's quantity squared, or it could be to the 4th power, 6th power. If it's even, well, you could have this scenario or this scenario. Again, this is going to be based on the entire function, but let's just keep it simple and say, as you approach a from either the left or the right, what's going to happen is the y values are approaching positive infinity. That's because there's no sign change from one side of this guy to the other side of this guy. And I'll explain with a full example in a moment. You could also have this situation right here. Now, let's say your n value is odd. Again, we saw this with f of x equals 1 over x. Well, now you do have a sign change from one side of this guy to the other side. So as we approach the x value of a from the left, here you're approaching negative infinity. As you're approaching x value of a from the right, well, now you're approaching positive infinity. Over here, you could have this scenario as well. So as you're approaching x value of a from the left, we're approaching positive infinity. As you're approaching x value of a from the right, now you're approaching negative infinity. So this is when n is odd. All right, let's look at an example. So here we have f of x equals 1 over the quantity x minus 3 squared. So you notice we have our vertical asymptote here, which is x equals 3. So where does that come from? Again, you take your denominator, which in this case is x minus 3, quantity squared. You set that equal to 0, and you solve. So I think we all know the solution there is x equals 3. But again, you could just say x minus 3 here is equal to 0. You add 3 to both sides of the equation. And so this is going to cancel and you get x is equal to 3. So that's what produces this vertical asymptote here, because obviously if you plug in a 3 here, 3 minus 3 is 0, 0 squared is 0, 1 over 0 is undefined. Now get rid of this. And I want you to think about the fact that on this side of your line, x equals 3, and on this side of your line, x equals 3, there's not a sign change. In other words, you can say that y approaches positive infinity as x approaches 3 from the left, and then also y approaches positive infinity as x approaches 3 from the right. And you can really combine that and just say y approaches infinity as x approaches 3 from either the right or the left. It would not matter. So the behavior is coming from the fact that you have something that is raised to an even power here. Because if I plug in something on this side of the line x equals 3, well, really this down here, before I square it, would be negative. So if I plugged in, let's say, a 2, you would have 1 over, you would have 2 minus 3 like that, quantity squared. So this would be 1 over. This would be 2 minus 3, that's negative 1. This would be negative 1 squared. But the fact that I'm squaring a negative makes it a positive. So I get 1 over 1. So I end up with 2 comma positive 1. If I had something like f of x equals 1 over just x minus 3, well, now that point would be down here. And what would end up happening is you would have something that looks like that. So you'd have this and then this. But in this case, because it's squared, it's flipping that up here. So you have this going this way and this going this way. So that's really important to understand, because when we graph stuff, you want to look at this guy right here, which is the exponent, and see if it's going to be odd or even. In the case where it's even, you're going to get something like this. So now I have f of x equals 1 over, and I did x minus 3 quantity cubed. But again, if you did x minus 3, you could just say to the first power, it's going to be the same thing generally, where this guy goes like this and this guy goes like this, because now you have a sign change on one side of this guy to the other. So here again is your x equals 3. That's your vertical asymptote. And now if you plugged in a 2, where you're going to get a negative 1. So 1 over, let's say 2 minus 3, and this is quantity cubed. Well, this equals 1 over, you can have negative 1 cubed, and now this is going to stay negative. Negative 1 cubed is still negative 1. So you get 1 over negative 1, which is negative 1. So this guy is down here now. So for this one, y goes to or approaches negative infinity as x approaches 3 from the left. So as we're coming from the left. Then y approaches positive infinity as x approaches 3 from the right. Again, this is because this is odd and you have a sign change on one side of the sky to the other side of the sky. All right, let's think about the final piece of the puzzle here. So we have the behavior of graphs of rational functions near the zeros of the numerator. So I want you to recall from our lesson on graphing polynomial functions that the behavior of the graph of a polynomial function near one of its zeros will depend on whether the multiplicity of the zero is even or odd. So again, you can go back to that lesson if you want more detail. In the case where the multiplicity of the zero is even, we saw the graph would touch the x-axis and turn around. That's because there's no sign change on one side of that guy to the other side of that guy. In the case where the multiplicity of the zero is odd, we saw the graph would cross through the x-axis. That's because there is a sign change on one side of that guy to the other side of that guy. So the same concept will apply when graphing a rational function. So let f of x be a rational function that is defined by a rational expression in lowest terms, or again, we could say simplified. This means that we will not have a common factor that we can cancel between the numerator and denominator. So you won't have to worry about having a hole in the graph. If n, which will be our exponent, is the largest positive integer such that you have this x minus k quantity raised to the power of n, if that is a factor of the numerator of f of x, the graph of our rational function will look different based on whether the n value is even or odd. All right, so let's look at two examples of this, just so it makes sense, and when you're graphing, you'll know what to do. Essentially, you're going to look at this f of x equals the quantity x minus 3 squared over x minus 2, just using a little table. The way you set up your table is you think about what are your vertical asymptotes. In this case, you just have one, so one vertical asymptote. And then what are your x-intercepts? In this case, you just have one x-intercept. So how do you get the vertical asymptotes? You set the denominator equal to 0, and you solve. In this case, you have x minus 2. Set that equal to 0, you get x equals 2, so you get a vertical asymptote here, which is x is equal to 2. Then for the x-intercepts, you take your numerator, you set that equal to 0, and you solve. So you have x minus 3 quantity squared equals 0. You solve that, you get x equals 3. So that's why you're going to have this 3 comma 0 here. Now, because the multiplicity of this guy is going to be 2, right, because the exponent there is 2, what's going to end up happening is you're not going to have a sign change on this side of this guy to this side of this guy. So when your graph goes to this 3 comma 0, it's going to touch and then turn around. It's not going to cross through the x-axis. Let me get rid of all this highlighting and let's focus on this over here. So you'll notice that I have a little table and I have anything less than 2. So anything less than 2, anything between 2 and 3, and then anything greater than 3. So you'll notice for this guy up here in the numerator, x minus 3 quantity squared, you'll see positive, positive, and then positive. So where does that come from? That's the fact that this guy is squared. So again, no matter what I plug in there, unless it's 3, when I square it, I'm going to get something positive. Because if the result of this is negative, when I square it, I get a positive. If the result is positive, I keep a positive. If I plugged in a 3 there, 3 minus 3 is 0, 0 squared is 0, but that's only going to be for right there. Everywhere else, this guy is going to be positive. Now, for this guy right here, this x minus 2, that's pretty simple. You just say x minus 2, where is that less than 0? You add 2 to both sides of the inequality. This cancels. You get x is less than 2. So anywhere where x is less than 2, so this is x equals 2 right here. So if I'm to the left of that, well, the x minus 2 down here would be negative. And so you see that you have a negative right here, and then everywhere else it would be positive. So positive and then positive. Well, with a fraction, again, a positive over a negative, that's going to give you a negative. So you'll see that where we're less than 2, so to the left of this guy, the function values are negative. And so let me erase all this highlighting. I'm just going to highlight this. You'll see that your function here, the values are negative. You're below the x-axis. Then what happens is everywhere else, so between 2 and 3, and then anything greater than 3, the function values are positive because, again, you have a positive over a positive in each case. The only exception to that is when the x value is 3, that's going to give me a y value of 0 or a function value of 0. So this guy right here is going to be positive, positive, positive. We're going to go to an x value of 3. And so we're going to have a function value of 0. So we're going to be on the x-axis, or we're just going to touch, and then we're going to turn back around because the function values are going to be positive, positive, positive. So it's just something important to understand when you're graphing these guys to know the behavior of this, whether or not it's going to touch and turn around or go through. Now here's an example of where it would cross through because you will have a sign change from one side to the other. So now I have f of x equals x minus 3 over x minus 2. So you're going to have the same vertical asymptote here, which is x equals 2, and you're going to have the same x-intercept, which is 3, 0. So I have the same intervals here, so anything less than 2, between 2 and 3, and then anything greater than 3. But what's going to change is that this guy in the numerator, even though you set it equal to 0, x minus 3, set that equal to 0, and you solve, you still get x equals 3. The multiplicity of that 0 is 1, which is odd. So if you look at this, x minus 3, let me just set this up. Where is that less than 0? You add 3 to both sides of the inequality there. This would cancel, you get x is less than 3. So in this interval and this interval, it's going to be negative, and then in this interval, where we're greater than 3, it'll finally be positive. In terms of x minus 2, we already know that that's negative in this interval, and then positive in this one and this one. So now, where x is less than 2, we have a negative over a negative, which gives us a positive. Let me erase everything. So that's going to be where x is less than 2. You can see the function values are positive. So that's why we are above the x-axis. And then for this one, between 2 and 3, you're going to notice that you have a negative over a positive, which is negative. So that's going to be this piece right here. You would see that the function values are negative. We're below the x-axis. And then if you come to where we're greater than 3, you have a positive over a positive. Well, that's a positive. So notice that where x is greater than 3, the function values are positive, so we're above the x-axis. So notice that what's happening is you're coming from below the x-axis, and now you get to 3, 0, you're on the x-axis, and then after an x value of 3, or to the right of that, where you're crossing through, you're above the x-axis. So that's why this guy is going to cross through, because there's a sign change from this side to this side. Whereas with this one, there was no sign change, right? We were going to come down here, positive, positive, positive. We get to a y value of 0. We're going to touch here, and then we're going to turn around, positive, positive, positive. That's the difference between the two situations. All right, let's look at the procedure for graphing a rational function. So we have f of x is equal to p of x over q of x, where q of x, this guy in the denominator, is not 0. P of x and q of x are polynomials, and the rational expression is in lowest terms. So I'm going to highlight that because that's important. Remember, we talked about what would happen if we have to cancel and we have a hole in the graph. So that's not going to apply here. We're going to be looking at things that are already simplified or in lowest terms. So the first thing you want to do is find and sketch all asymptotes. The second thing is to find the x and y intercepts. We know that the y-intercept would occur at 0, f of 0, and the x-intercepts would occur at k, 0, where k is a 0 of the numerator. In other words, you're taking the numerator, setting it equal to 0, and solving. The solutions there would correspond to x-intercepts. Then for the third thing, we're going to determine whether the graph will intersect its non-vertical asymptote. So if it exists, a lot of times if you get a horizontal asymptote of y equals 0 or the x-axis, well, you don't need to do this because you've already figured out if you have an x-intercept. And so this would be already done for you. There's other scenarios. You might get a horizontal asymptote that's maybe y equals 2 or a slant asymptote, something like that. In that case, you'd have to take this additional step. Then the fourth thing is we want to split the number line up into intervals based on the x-intercepts and vertical asymptotes. We're going to pick an x value in each interval, then find and plot the related point. This right here where it says pick an x value, you might need to pick several. It's just depending on what you're trying to graph. Some graphs are more complex and they take more points. But for a basic rational function, something that's easy, you can just use one x value in each interval, and that would be okay. Then for 5, the last thing, we're going to just sketch the graph. All right, let's start off with f of x equals, we have x minus 1 over x squared minus 6x plus 8. The first thing I'm going to do is find the vertical asymptotes. Take the denominator, set it equal to 0, and solve. So if we factor this, we get the quantity x minus 4 times the quantity x minus 2, set that equal to 0, 0 product property, x minus 4 equals 0, or x minus 2 equals 0. We solve each one, you get x is equal to 2 or 4. So those would be your vertical asymptotes. Then in terms of your horizontal asymptote, in this case, I want you to notice that the degree of the numerator is 1, the degree of the denominator is 2. So what's the rule? If the degree of the numerator is less than the degree of the denominator, you will have a horizontal asymptote, which is the x-axis or the line y equals 0. Now, in terms of your x-intercept, because you're only going to have one here, you take your numerator, which is x minus 1, you set that equal to 0, and you solve. So you get x equals 1. So the x-intercept is going to occur at 1, 0. Then for your y-intercept, you're going to plug in a 0 for x. So f of 0, that would be equal to 0 minus 1 over 0 squared minus 6 times 0 plus 8. So if you simplify, this would be equal to negative 1 over 8. So your x-intercept occurs at 0, negative 1/8. All right, so I have everything summarized here. So you have a vertical asymptote, which is going to be x equals 2, then another that would be x equals 4. So this is your x equals 2, and this is your x equals 4. Okay, coming back, you have a horizontal asymptote, which is y equals 0. Now, I don't label an asymptote if it's the x-axis or the y-axis. You can if you want. So I'm not going to put anything there, but if you wanted to label this and just do something like y is equal to 0, and you could put horizontal asymptote on your page, that's fine. A lot of teachers will let you do that, or you can make a dashed line there, whatever you want to do. Okay, the x-intercept, we know that occurs at 1, 0, and the y-intercept occurs at 0, -1/8. So this is a little bit hard to see because of the font, but this right here is your 1, 0. That's going to be your x-intercept. And so that's also the point where we're going to intersect that horizontal asymptote. So again, when that happens, if you have an x-intercept like we do in this case, and you have a horizontal asymptote, which is the x-axis or the line y = 0, you don't need that extra step like we talked about in the procedure. We already know it's going to cross through right there. Then the other guy was this one right here. So this is 0, -0.125. That's just -1/8 as a decimal. And then coming back, I have some additional points. I'll talk about those in a moment. So we split the number line up into intervals, again, using the vertical asymptotes and then the x-intercept. So you can have anything less than 1, you're going to have between 1 and 2, then between 2 and 4, and then anything greater than 4. So just pick an x value that's in the interval and plug it in and get the y value. I went ahead and grabbed some stuff that was easy to work with. A lot of times when you do this, you don't know what's easy to work with. So just plug it into your calculator, and if it's a nasty decimal, just round it to the nearest hundredth or the nearest thousandth. Whatever you want to do, you're just trying to get an idea of what this looks like. It does not have to be perfect, so do not worry about that. So this guy is going to be -2, -0.125. Then this guy is going to be 1.5, 0.4. This guy is going to be 3, -2. This guy is going to be 4.5, 2.8. So coming back, that's going to be these points. Let me just highlight them. So this is your -2, -0.125. Then this one is going to be your 1.5, 0.4. This one's going to be your 3, -2. And this one's going to be your 4.5, 2.8. Now, you're going to see that I listed, let me erase these, some additional points. So I put in 2.5, -2. That's going to be right there. And then I put in 6, 0.625. I just put those in to help. You don't need them, but sometimes with a shape like this, you want them. It just makes it a little bit more accurate. So you'll see I put those as additional points. So 2.5, -2, and then 6, 0.625. This one right here is probably the hardest thing to get. We have not taken calculus yet, so we don't know about derivatives and the first derivative test and all those different things. So finding the local maximum point, like I talked about with graphing polynomial functions, is a challenge. So you can actually do it and get somewhat close by just plugging things in. So you could plug in 2.5, 2.6, 2.7, 2.8, and just look at the y values that you're getting, and you can get close to this. It does not have to be perfect, but the idea is that you're going to have to turn. Now, putting things together, we know that this guy right here, this x = 2, and this guy right here, this x = 4, those came from zeros that had a multiplicity which was 1. So that's an odd multiplicity. So what does that tell me? When I look at this guy right here going up, that means this guy is going to be going down. And when I look at this guy right here going up, that means this guy right here is going to be going down. And that's the toughest part here is you know you're going to turn, but you just don't know where. And that's where that approximation comes in. Again, I've already given you this, the local maximum point. So 2.732, -1.866. That's an approximation, but it lets us know that we would turn somewhere like this. So something like that. And then this part right here, it's actually important to get right. We know that we're going to cross through the x-axis right here, because again, that 0 that's associated with that x-intercept has a multiplicity of 1. So we know we're crossing through right there. That means we're crossing through the x-axis or the horizontal asymptote, which is y = 0. So it's going to go like that. It's going to come down, and then it's going to come back up, and it's going to keep getting closer and closer to 0 as we have x values that go out to -infinity. And I know that's not drawn straight, but I'm just not a good drawer. Then this piece right here would just come down here. On this piece, it's not going to actually intersect the x-axis. It's just going to get closer and closer to it without touching. And I know I'm a bad drawer. Let me show you a computer-generated version, which is obviously much better. So you can see that this piece right here, it's coming down, and you can zoom in on Desmos, it's a little bit better. It's going to cross through here at 1, 0, and then what's going to happen is it's going to come down a little bit, and then it's going to start coming back up, and it's going to approach the x-axis, but it's not going to touch it, right? It already crossed through here, but once it crosses through, it does not touch it again. It's just going to keep getting closer and closer as we go that way. This piece right here, again, this goes down, comes up, makes its turn, goes back down, and then this piece right here, we're going down like this, and we're approaching the x-axis, but we're never actually going to touch it. All right, let's look at the next one. So here we have f of x equals x squared minus 4x plus 4 over x minus 1. So again, take the denominator, which is x minus 1, set it equal to 0 and solve. So you get x equals 1. That's your vertical asymptote. Take your numerator and set that equal to 0. We're doing that to get the x-intercept. So x squared minus 4x plus 4 equals 0. You can factor that. This is the perfect squared trinomial. That becomes the quantity x minus 2 squared equals 0. So if you solve that, you just get x is equal to 2. But keep in mind that this is squared. So the multiplicity of that 0 is 2. And so this x-intercept, which is 2, 0, we're going to touch and turn around there. For the y-intercept, plug in a 0 for x. So you get 0 squared minus 4 times 0 plus 4 over 0 minus 1. So this equals negative 4. So you're going to get 0, negative 4. Now, in terms of the horizontal asymptote, you are not going to have one because the degree in the numerator is 2 and the degree in the denominator is 1. So if the degree in the numerator is greater than the degree in the denominator, you will not have a horizontal asymptote. But if the degree in the numerator is exactly 1 more than the degree in the denominator, you will have a slant or oblique asymptote. Again, we know how to do this already. We set up some long division. So this coefficient is a 1. That's why you have a 1 there. This is negative 4, and then this is a 4. So 1, negative 4, and 4. This is in the form of x minus k. So your k here is 1, so that goes out here. Drop this down. 1 times 1 is 1. Negative 4 plus 1 is negative 3. 1 times negative 3 is negative 3. 4 plus negative 3 is 1. So you get 1 as the coefficient for x. Because again, if this is squared, this becomes to the first power. You drop it by 1 degree. Then you have minus 3 and then plus. This is your remainder, and that goes over the divisor or the denominator. So this becomes x minus 3 plus 1 over x minus 1. So remember from earlier, this is the part you're going to focus on. Because as x goes to positive infinity or negative infinity, this part right here is going to go to 0. So what's happening is you're getting closer and closer to that line, which is y equals x minus 3. So let me write everything out for you. We have a vertical asymptote, which is x equals 1. We have a slant asymptote, which is y equals x minus 3. We have an x-intercept, which is 2, 0. We're going to touch and turn around there. And then we have a y-intercept, which is 0, negative 4. I have split the number line up into some intervals. Again, anything less than 1, between 1 and 2, and then anything greater than 2. And I have some points. So negative 1, negative 4.5, 1.5, 0.5, and then 3, 0.5. So I'm going to plot these in a moment. I want to talk about something that's a little bit time consuming. So you heard me mention that if you had a horizontal asymptote and it was the line y equals 0 or the x-axis, if you find the x-intercept, you really don't have any more work to do there because you know what's going to happen in terms of if you're going to cross your horizontal asymptote or not. When you don't have that situation, then you have to do some work. So you're going to take your function here, so x squared minus 4x plus 4 over x minus 1, and you're going to set that equal to your slant asymptote, which was x minus 3. So keep in mind that you're trying to solve for the x value where those two y values or those two function values, you could say, would be equal. So to do this, you would multiply both sides by x minus 1. So you'd have x squared minus 4x plus 4 is equal to x minus 3 times x minus 1. All I did was I multiplied both sides by x minus 1. If you simplify over here just using FOIL, you're going to have x squared minus 4x plus 3, and then you'll notice that this would cancel away. You just subtract x squared away from each side. If you add 4x to both sides, that's going to cancel away. You're going to be left with 4 equals 3, which is a false statement. So we know that when this happens, you have an equation with no solution, so we will not intersect that slant asymptote. Okay, so just coming down and putting everything together on the graph, this is your negative 1, negative 4.5. This is your 0, negative 4. This is your 1.5, 0.5. This is your 2, 0. This is your 3, 0.5. This is your vertical asymptote, which is x equals 1. And then this is the slant one, which is y equals x minus 3. So pretty much this one's very easy to do. You know that right here, this is going to touch and turn around. So this would do something like this, like that. Touch and turn around like that. Again, as the x values go out to positive infinity, this is approaching that line y equals x minus 3. So that's how I know about this and this. When we think about the vertical asymptote here, which was x equals 1, that came from a 0 that had a multiplicity of 1. So I know that this guy right here is going to go like that because this one goes like that. And then this is going to turn here and then come back. And again, as x decreases without bound, this is going to approach the line y equals x minus 3. Again, we could just check the computer-generated version, which is a lot easier to see. So again, this guy right here is going to come down, touch, and turn around. Again, as x approaches positive infinity, this approaches that line y equals x minus 3. And then down here, you'll notice that again, because this is going up, this is going down here. So this is going to come, and it's going to turn here, and it's going to approach that line, which is y equals x minus 3 as x goes to negative infinity. All right, let's look at one more. So now we have f of x is equal to x minus 2 over x minus 3 quantity squared times x minus 1. So for the vertical asymptotes, you take your x minus 3 quantity squared times x minus 1, and you set that equal to 0. And you could just do x minus 3 equals 0. So the solution there is x equals 3, or x minus 1 equals 0. The solution there is x equals 1. But notice that again, this is squared. So this right here, when you look at that vertical asymptote, you have to be very, very careful because you're going to have, let me just show you the graph. This is your x equals 3. Again, like we saw with y equals x squared, you have, let me actually erase this and show you, this guy right here, as x approaches 3 from the left, y is approaching positive infinity. And then as x approaches 3 from the right, y is approaching positive infinity. Again, that's because the multiplicity of that 0 was 2, and that's even, so that's what's creating that. There's not going to be a sign change on one side of that guy to the other side of that guy. So that's one of the most important things to understand with this, because if you don't get that, you might end up drawing this wrong. Coming back up here, let's get the x and y intercepts. So the x-intercept, again, you just take your numerator, x minus 2, set that equal to 0 and solve. You get x equals 2, so it's 2 comma 0. For the y-intercept, you just plug in a 0, so f of 0 is equal to 0 minus 2 over 0 minus 3 quantity squared times 0 minus 1. So if you simplify this, you're going to get this is equal to 2/9. So 0 comma 2/9. And just putting everything together, you have a vertical asymptote, which is x equals 1, and then also x equals 3. Again, this one right here is the one you want to put a star next to or something like that, just saying that the multiplicity of that 0 was 2. It's even, so it's going to have a different behavior than the other one. The horizontal asymptote is y equals 0, and that's because the degree of the numerator is less than the degree of the denominator. Then the x-intercept is 2 comma 0, the y-intercept is 0 comma 2/9. Again, splitting up the number line into intervals, you have anything less than 1, anything between 1 and 2, between 2 and 3, and then anything greater than 3. These are just things that I picked out. Again, if you're picking something or you're working with decimals, don't worry about if you get something that's nasty, just round it and move on. So I have 1/2 comma 12 over 25. I have 3/2 comma negative 4/9. I have 5/2 comma 4/3, and then 4 comma 2/3. Okay, putting everything together, here's your 0 comma 2/9. Here's your 1/2 comma 12 over 25. This is your 3/2 comma negative 4/9. This is your 2 comma 0. This is your 5/2 comma 4/3, and then this is your 4 comma 2/3. So again, I know with this guy right here, the multiplicity was even. So that tells me this is going to go up like this, and then this is also going to go up like this. And so I can draw this. I know that the horizontal asymptote is going to be this guy right here, so it's going to approach the x-axis but not touch it. Again, because the x-axis or the line y equals 0 was the horizontal asymptote, we already know it's going to intersect right here at 2 comma 0, but it's not going to intersect anywhere else. Now, in terms of this one, again, this multiplicity of this was odd. So that means that if this guy is coming up like this guy is going to go down like this. So then you can just connect this like that, and this piece right here becomes going down like this, and again, approaching the x-axis but not touching. Again, looking at the computer-generated version, you're going to have this piece right here, again, coming down, approaching the x-axis but not touching. This right here is going to look like this. Again, this is where we're going to cross through the x-axis. Remember that the multiplicity of that 0, when we got 2 comma 0, that's 1, so that's why we're going to cross through. And then this right here is going to approach this way, and this is going to approach this way, and then this guy right here is going to come down and approach the x-axis but not touch it.